Palka was born in Poland, in Czechia, and he studied electrical engineering at my university in Braunschweig. He did lots of activities outside of the university, including he was in Israel to do a practical term there. He is now a researcher in my team, and his work is on the use of dynamic broadcast for white space use, and he will present his presentation about white space and dynamic use case now.
Thank you, Mr. Reimers, for the kind introduction. Ladies and gentlemen, welcome to my presentation, Allocation of Dynamic TV White Spaces in a Dynamic Broadcast System. The talk is structured as follows. I will first give a short introduction and the motivation to TV white spaces and spectrum demand by different kinds of users. I will then move on to another type of TV white spaces, which is the dynamic TV white space. These are a special form of TV white spaces that occur in a dynamic broadcast system. I will tell a few words how to manage this dynamic spectrum in a dynamic broadcast system, which is by means of the dynamic TV white space database. I will then present our system demonstrator, concentrating on the issue of spectrum management. I will end my presentation with a conclusion. So let me start with a rather simple statement that terrestrial frequency spectrum is an important resource for wireless communication systems. We heard some of it already from Mr. Reimers. The problem is that frequency bands that are usable for mobile communications are today almost completely allocated to different kinds of wireless networks. But on the other hand, if we take at the spectrum usage more closely, we will see that many frequency bands are underutilized, which is also the case in the TV spectrum, in the UHF bands. So we see here the map of Germany, where we have calculated the number of locally not used TV bands. So these are regions where there is no TV service and at a certain frequency. This is due to network and interference planning and the use of high transmit powers in terrestrial broadcasting. So these frequency bands are a potential resource for future wireless communication systems, and you see regions where basically all of the available channels are free. On the other hand, some regions may provide less TV white spaces, but nevertheless, this seems to be an important resource. But if we would like to introduce a secondary use of this spectrum, we'll have to deal with the propagation issues of the secondary user. So this is usually taken into account by means of a safety distance to the coverage area of the broadcaster. And you see here two cases. In the first case, we assume a secondary user with a rather small transmit power, and this would correspond to, let's say, 1 kilometer safety distance. And compared to the figure before, you see the number of white spaces has reduced. If we then again increase the transmit power to, let's say, 1 to 2 kilometer safety distance might be more appropriate. And you see now the number of available TV white spaces has reduced drastically. Still, there are some regions with a lot of TV white space channels available, but now again, in certain regions there might be not enough secondary white space spectrum for an efficient use. So today's TV white space availability and capacity may not be sufficient for secondary wireless communication systems. Furthermore, A cooperative network usually is desirable, where all the spectrum users somehow cooperate to use the spectrum in the most efficient way. And this is where dynamic broadcast comes into play, because dynamic broadcast offers additional frequency resources on a time-to-right basis, which we call dynamic TV white spaces. And these locally reusable frequency bands can be now actively given to an interested user like a Wi-Fi network operator and so on. So you have seen this block diagram already, so I will go quickly over it. You see on the left-hand side the user terminal of the dynamic broadcast system, which is now connected to a terrestrial broadcast network and a broadband network, and can receive TV services equally over both channels. So via this network connection, there is a return channel to the broadcast network by this monitoring and signaling block. And the key component now is the decision logic, which is able to reconfigure all the parts of the system dynamically. This includes the reconfiguration of multiplex configurations and the transmission parameters of the broadcast network. Furthermore, the decision logic can decide whether to provide a certain part of the TV program live, or maybe in advance if it's not a live program. So if and when all these parameters are reconfigured dynamically, the spectrum usage is also dynamic. So in dynamic broadcast, we provide an interface to secondary wireless networks by means of a dynamic whitespace database, which I will introduce in a few moments. And this could be, for instance, used to increase the capacity of a 2.4 gigahertz wireless hotspot by means of this TV spectrum. So now we have to extend the definition of the TV whitespaces, which usually is given by a frequency, a position, a permitted transmit power, and now includes the dimension of time. So in this example, we see a map, a coverage map with a broadcast transmitter operating at 2 different frequencies with 2 different coverage areas. And on the other side, there is a secondary user which might use a larger frequency band, here corresponding to frequency band 1 and 2. And now this is time point T1, but at another time point T1 plus X, the configuration might have changed. So the broadcast transmitter now is only operating at the frequency 1, and as a result, the secondary user now has the possibility to use more white space. For the management of TV white spaces, usually a geolocation database concept is used. And in order to handle these dynamics that I've just spoken about, we have developed a special geolocation database concept, which is the dynamic TV white space database. So basically, all spectrum information is stored in such a database, but the dynamic content, which always includes a start point and an end point or a time duration for availability, stored, and this is always handled by the so-called spectrum server. The spectrum server, at the same time, provides the possibility to all spectrum users to communicate with each other. So now it is possible that a secondary user, for instance a Wi-Fi operator, can formulate spectrum requests by means of the spectrum server, and these spectrum requests are then forwarded to the dynamic broadcast network, which is the primary user, and the decision logic can then decide to adapt the network parameters accordingly. come to our system demonstrator that is shown here at IFA, at the TechWatch Hall, starting with an overview. So we present the whole system. On the one side there is the network management, which is basically the dynamic layout center, where the TV content may come over broadcast or broadband and is delivered to a user terminal, which is responsible for combining all these media sources in such a way that the TV viewer doesn't notice any interruptions. By means of this broadband connection, signaling messages can be exchanged so that the user terminal can perform all the network-initiated switches seamlessly. Here on the right-hand side, there is the secondary user of the demonstration, which is a base station and a mobile white space device. So it's a master-slave configuration where the base station is connected to the network management of the dynamic broadcast network. And via this connection, it is easy to implement the dynamic TV whitespace database. Here, this mobile device is interested in a file downstream from the base station, and this usually happens by means of this wireless LAN connection at 2.4 gigahertz. But in times when the dynamic broadcast network releases broadcast spectrum, we have additional capacity available for the downstream via the TV spectrum. So what is shown here is that in a dynamic fashion, the downstream data rate can be increased. So I will now go more into detail of the secondary user side. So this is the base station, which basically consists of a file server and a decision block that decides which path to use for the downstream. This could be the wireless LAN at 2.4 gigahertz via this TCP server, or it could be in addition via the UHF band, and this is realized by means of a software-defined radio. And parts of the demonstration include new radio libraries. This is mainly this modulation block, which includes PAM modulation and OFDM and so on. So here is a USRP board from Ethos that transmits at 554 megahertz. This data routing block is connected to a signaling and configuration block, which directly speaks to the dynamic broadcast core network. And here the dynamic TV whitespace database is implemented where spectrum information can be exchanged. So for the mobile whitespace device, in addition to the downstream via wireless LAN, a signaling port is provided to forward the corresponding spectrum information to the whitespace device, which is shown here. So we have the data port, the signaling port, and dynamically, temporarily, we have in addition this downstream via the TV spectrum. The demodulation block consists of the OFDM calculation and so on. And then a combined data rate is calculated and displayed on a screen. And this can be shown, can be seen here. This is the state 1 of the demonstration, where temporarily the DVB-T network is operated at the primary side. So we have only wireless LAN connection at 2.4 gigahertz, resulting in maybe something like 20 megabits per second in this case. It's rather difficult here at IFA to establish such a good connection, so if you come to our hall, you will see something like 10. In the next state, we have shut down the DVB-T transmission and we come back with a signal that looks quite similar, but is now the extension of the wireless network to increase the data rate, and you see a much higher data rate as the result. So now comes the conclusion. In addition to static TV white spaces, dynamic broadcast offers more frequency resources now on a time-variant basis, and these dynamic TV white spaces are managed by means of the dynamic TV white space database which we have developed. I have shown the complete system demonstration setup, and it is shown that although the TV viewer can receive a continuous and uninterrupted TV service, the spectrum is shared dynamically, and there is a benefit of capacity increase for secondary users. And now I would like to cordially invite you to our hall to see the live demo. Thank you very much.
Ladies and gentlemen, do we have any questions for Piotr Palka? He started with these static white spaces, where of course one of the things ongoing worldwide is that in many organizations people try to exploit those static white spaces. Which means that in areas where you have a lot of TV coverage, the white spaces may not be available. Can you give us an indication of what you think, like for example in a highly populated area where the spectrum is really scarce, the difference between static white spaces and dynamic white spaces can end up? So what would you gain?
Yes, we have analyzed some certain regions where we believe that TV white space capacity may not be sufficient, which is, for instance, Frankfurt, where we had something like 3 white space channels available, and by means of dynamic broadcast, if we can temporarily provide 3 more TV white space channels, which is realistic, then the gain is 100%.
For those of you who are not really involved in this kind of business, there was an auction of TV spectrum in Germany just recently, where the cellular network operators paid 3.6 billion euros for 72 megahertz of spectrum. 3.6 billion. So if Piotr Palka releases 3 channels, 8 megahertz each in Frankfurt, we expect that we will have an income of 1.2 billion euros, which is not bad business. All right, thank you again.